Welcome to the Language Year, Comprehensible Input for Learners. Today, we're diving into one of humanity's most captivating questions. Are we alone in the universe?
Before we jump in, we want to mention that this debate isn't meant to cause controversy. It's meant to educate, especially for those learning English or anyone fascinated by the possibility of life beyond Earth. This debate is here for you.
Yeah, absolutely. So the core tension we're tackling today, it really emerges from, everything we're observing. It's maybe the biggest puzzle in astrobiology, the Fermi Paradox. I mean, the universe is unbelievably vast, ancient. Seems like there should be endless chances for life, right? But all we hear is silence.
A really profound silence.
Exactly. And my position, look, it's one of determined scientific optimism. I really think life is likely, everywhere, ubiquitous across the cosmos. You just look at the sheer number of planets, how tough biology actually is, and the fact that the basic ingredients for life are just out there. I think we're genuinely on the verge of finding something. That silence, it's just temporary, a limit of our current tech.
See, I come at it from a different angle. That optimism is definitely compelling, I get it, but just because something is statistically possible doesn't make it real, right? It's not empirical proof. I actually contend that the silence itself, that's the most critical piece of data we have. It strongly suggests that complex, detectable life is exceedingly rare. I lean towards the idea that Earth is a true cosmic anomaly, shaped by the really specific conditions of the rare Earth hypothesis. And maybe there's some massive evolutionary hurdle, what people call the Great Filter, that just stops most life from ever getting smart or, spreading out.
Okay, but let's start with scale, though, because that just immediately undercuts the idea that we're unique. The observable universe, estimates are now maybe 2 trillion galaxies. 2 trillion. Then you calculate the stars, the numbers they dwarf comprehension. And now we know planets are pretty much the norm around those stars. So you gotta conclude there are more planets out there than grains of sand on every single beach and desert on Earth combined. Seriously. To think that out of that massive cosmic lottery, life only hit the jackpot once, right here. I mean, statistically, that seems unsound. Almost absurd, wouldn't you say?
Okay, but relying purely on sheer scale, isn't that a bit of a statistical fallacy? You're kind of assuming that quantity automatically guarantees quality. You're assuming life is easy to start, easy to keep going, and easy to evolve into something we could actually detect. That's a lot of assumptions.
Well, I don't think it's just an assumption. That's where the biology, the actual data we have, provides real evidence. Look at Extremophiles. I mean, these are absolutely bonkers organisms, right? They thrive in conditions we used to think were instantly deadly. You've got thermophiles living in boiling deep sea vents, acidophiles just happy as can be in stuff like battery acid. What this shows critically is life's incredible resilience. It's not some delicate flower needing perfect conditions. It's more like a tenacious weed that can grab hold wherever there's some energy and, some kind of liquid. This just radically expands what we should consider habitable.
I'll grant you that. Microbial life, it might be common. A tenacious weed, I like that analogy. But the Fermi Paradox isn't asking where are the microbes. It's asking where is the intelligent, galaxy-spanning civilization. If stars older than our sun had billions of years head start to produce technological societies, they should have had more than enough time to colonize the whole Milky Way, even if they traveled, super slowly. The fact that we haven't found any alien artifacts, no self-replicating von Neumann probes, and detected pretty much zero sustained, obviously intentional radio signals, that is the defining characteristic of the universe right now, the Great Silence. It demands a really profound explanation. And for me, the simplest explanation is that complex life is just incredibly rare.
See, I'm not convinced by that reasoning because the universe is already seeded with the raw materials you need. We know amino acids, the building blocks of proteins, they get made non-biologically out in interstellar clouds. The Murchison meteorite, it had over 90 different amino acids in it. proof they come from space. And complex organic molecules, things like ethylene glycol, they're everywhere. The cosmic recipe is universal. Essentially, every new world gets delivered a starter kit with the basic chemistry needed for life to begin, for abiogenesis.
Right, but having the ingredients in the cupboard is one thing. Successfully baking the cake is, well, another entirely. Especially when the cosmic oven is constantly trying to burn your creation or freeze it solid. This is where the rare earth hypothesis really comes into play for me. Okay, simple life may be common, but complex, intelligent life, that seems to require a whole series of extraordinary cosmic coincidences. You basically need to win the lottery multiple times in a row.
Like what specifically?
Well, first, you likely need a protective big brother, like our Jupiter, a massive gas giant way out there, sweeping up potentially deadly asteroids and comets, clearing out the debris field. Second, you probably need a large, stabilizing moon, like ours, which keeps our planet's tilt steady. Without that stability, Earth's climate would likely wobble like crazy, causing catastrophic climate shifts that could, sterilize the surface every few million years.
I agree the moon and Jupiter are significant for Earth as we know it. But are we absolutely sure those specific factors are required for intelligence to evolve everywhere? Especially if intelligence arises, say, in a more sheltered environment, not necessarily on a surface?
Well, that's the core of the argument, isn't it? Because the environmental checklist doesn't stop there. You probably also need active plate tectonics. Why? Because plate tectonics acts like a planetary thermostat, regulating CO2 through the carbonate-silicate cycle over huge timescales. Without that, you risk ending up like Venus, a runaway greenhouse, totally inhospitable. And finally, you need a molten core generating a strong magnetic field. That shield protects your atmosphere from being stripped away by the star's wind. If you miss even one of those steps, well, the Great Filter has likely claimed that world. So the silence we observe, it might just be the inevitable result of how incredibly hard it is to win that entire geological lottery.
That's an interesting way to put it, though. I'd frame it differently. That checklist seems very Earth-centric. It's focused entirely on creating a surface world exactly like ours. But here's what gets me excited about this. We're finding planetary stability might not be as rare as that list suggests, and maybe surface stability isn't even the main event.
How so?
Look at the exoplanet data pouring in. We're finding Earth-sized worlds everywhere now. Kepler 452b, they call it Earth's older cousin. It's been stable in its star's habitable zone for 6 billion years. That's way longer than life has even existed on Earth. And then you have systems like TRAPPIST-1, 7 rocky, temperate planets orbiting one star. Clearly, having planets in temperate orbits isn't some statistical fluke.
Okay, I hear you on the numbers of planets, but the type of star in those specific systems you mentioned, TRAPPIST-1, Proxima Centauri b, that introduces a massive filter right back into your optimistic equation. The most common stars in the galaxy, about 70% of them, are red dwarfs. And they are notorious for violent stellar flares, especially when they're young. These flares blast out huge amounts of radiation that can literally strip away planetary atmospheres and sterilize surfaces. So yeah, you might have a planet orbiting in the quote-unquote habitable zone, but it could easily be a cosmic radiation death zone instead. The star itself actively works against surface life.
Right, which is exactly why we need to think beyond planetary surfaces and focus more on interior environments. Even if many exoplanet surfaces are hostile, life could potentially persist, maybe even thrive in subterranean habitats or under thick ice shells where there's liquid water powered by internal heat. We have really compelling evidence for this right here in our own solar system. I mean, think about Europa, Jupiter's moon. It almost certainly has a saltwater ocean under its ice, maybe holding 2 to 3 times the volume of all of Earth's oceans combined. And it's kept liquid by tidal heating from Jupiter's gravity.
Okay, Europa's ocean is a strong possibility.
Or even better, Enceladus, Saturn's moon. The Cassini spacecraft flew right through plumes of water vapor erupting from cracks near its south pole. And what did it find in those plumes? Water, complex organic molecules, and, this is the clincher, tiny silica nanograins. Those silica particles are basically direct evidence of active hot hydrothermal vents on its ocean floor. So you've got the big three ingredients right there: liquid water, organic molecules, and a sustained energy source, all nicely protected beneath an ice shell. The conditions for microbial life in these ocean worlds, they completely bypass the need for a magnetic field or plate tectonics or a big moon.
It certainly stretches the definition of habitable, I agree. But it also introduces a perhaps even more challenging problem: the ambiguity of potential biosignatures and just how difficult it's going to be to get definitive proof from places like that.
But I think the difficulty of proof is actually falling away pretty rapidly thanks to incredible new observational tools. This is where something like the James Webb Space Telescope, JWST, is just revolutionary. We're moving beyond just finding planets, we're starting to chemically fingerprint their atmospheres. JWST detected methane and carbon dioxide on K2-18b, that sub-Neptune world. It suggests it might be what they call a Hycean world, basically, a water-covered planet with a hydrogen-rich atmosphere. Those could be potentially ideal environments for simple, widespread life.
Methane and CO2. Okay.
And we don't even need to look light years away. Look at Mars. The Perseverance rover, in its Sapphire Canyon sample, found organic carbon right alongside these very specific, kind of complex mineral features. They call them leopard spot minerals, things like vivianite and greygeat. Now, here on Earth, those particular mineral patterns are typically associated with microbial activity, with their metabolisms. Look, I get why people are cautious, I really do, but when you put the organics, the history of water on Mars, and that unique geology all together, that's starting to look like a pretty powerful potential biosignature.
I'm sorry, but I just don't buy that it's definitive yet. Let me tell you why. The burden of proof for claiming you found extraterrestrial life, it has to be extraordinarily high, right? Take K2-18b. Yes, there was that initial hint of maybe sulfur-based molecules like DMS, but that detection was always pretty tenuous, what scientists call 3 sigma significance. That basically means there's a non-trivial chance it was just statistical noise, or maybe an artifact from processing the data. And in fact, subsequent reanalysis has already cast serious doubt on that signal. Plus, non-biological processes, purely geological things like volcanic outgassing, can produce methane and carbon dioxide, and they can create complex mineral patterns too. Finding single gases or even weird minerals just isn't proof on its own.
And the same rigor has to apply to Mars. While those Che of all falls samples from Perseverance are definitely tantalizing, I agree, those complex mineral patterns and the organic carbon could also be produced through purely non-biological chemical reactions when water interacts with rock over long periods. The definitive test, the absolute proof we need, really requires getting those cache samples back to Earth with the Mars Sample Return mission. We need to analyze them in sophisticated labs here, look for things like specific isotopic ratios that strongly indicate biology. Until we have those rocks in hand, those findings are just, well, they're ambiguous clues. Interesting, but ambiguous.
Okay, that high burden of proof is fair. But doesn't that just highlight why the search itself needs to evolve? If confirmed biosignatures are going to be so inherently ambiguous and subject to years of debate, maybe we should also be putting more effort into looking for technosignatures, signs of intelligence, which would presumably be far less ambiguous if we found them, and our ability to search is expanding exponentially, basically following Moore's law. SETI, the search for extraterrestrial intelligence, has barely scratched the surface of the cosmic haystack so far. Some astronomers, like Seth Shostak, are estimating that if we keep improving our listening capabilities, we should actually detect a signal within maybe the next 2 decades. 2 decades? That sounds optimistic.
Well, and maybe it's not just radio signals. Think about it. If civilizations survive long enough to become detectable across interstellar distances, they're probably going to be highly advanced, maybe even post-biological, some form of artificial general intelligence. And these advanced entities, they might actually be easier to spot, not through faint radio whispers, but through more obvious technological signs, like massive engineering projects. Think astroengineering, like partial Dyson spheres or swarms built to capture a huge amount of their star's energy, things that would leave a noticeable, unnatural fingerprint on the light we receive.
Whoa, okay, that requires an enormous leap of faith, though. And it kind of ignores the profound practical limits imposed by just the sheer tyranny of distance and time. Even if, let's say, 10,000 technological civilizations currently exist scattered across our galaxy. The average distance between them would still be hundreds of light years. We've only been capable of sending out powerful radio signals or listening for them for about a century, a tiny blip in cosmic time.
Right, but
Think about the synchronicity required. For us to have a two-way conversation, another civilization would have to be incredibly close, like within maybe 50 light years, and be actively broadcasting during our tiny, century-long window of being technologically capable. If they're farther out, say 500 light years away, they could have sent a powerful message 500 years ago, aimed right at us, and we wouldn't even receive it for another 400 years. The vast gaps in both space and time make intentional detection incredibly difficult.
Mm-hmm.
And focusing on something as speculative as like a partially built megastructure, hundreds or thousands of light years away, a Dyson swarm fragment, that's also loaded with ambiguity. How could we ever be sure? It seems far more rigorous scientifically to prioritize getting localized confirmed evidence, whether that's complex biosignatures proven by Mars sample return, or detecting a sustained, unambiguous, clearly artificial extraterrestrial radio signal. I worry sometimes that over-optimism about finding, alien megastructures kind of distracts from the really hard, rigorous work of local verifiable science.
you know what? You're absolutely right that rigor is key, and I do acknowledge the incredible gravity of that great filter concept. If the major bottleneck is something in our past, like the hugely complex leap from simple prokaryotic cells to complex eukaryotic cells, the jump needed to even start building multicellular life, then yeah, we could be statistically very rare, and the silence would be tragically logical, that is.
That's a truly sobering perspective. And on my side, I have to acknowledge the contagious excitement you bring when talking about these potential ocean worlds. The evidence for active hydrothermal vents on Enceladus, finding the organics, the water, the energy source, altogether it proves the universe is probably far more dynamic and creative in nurturing potential life-supporting niches than the strict conditions of the classic rare Earth hypothesis might suggest. It definitely suggests that focusing only on Earth-like surfaces might be too narrow a view.
So yeah, the central disagreement really remains over how we interpret that silence, doesn't it? My conviction, it really stems from the sheer statistical weight of all those planets, combined with the proven tenacity of biology. It just points towards a cosmos that should be teeming with life, at least simple life. And the fact we haven't found it yet, I see that as merely a temporary observational challenge, one that our new missions and better technologies are poised to break, maybe soon.
And I maintain that while, yes, the universe is clearly teeming with potential habitats, the unique confluence of geological factors, gravitational stability, and sheer evolutionary luck needed to create not just life but complex, long-lasting technological civilization, well, that remains totally unproven anywhere else. And until that concrete proof arrives, the profound silence makes Earth seem exceptionally special, maybe even unique.
Whether you lean towards my abundance model or you favor the rarity model, this whole debate is it's essential. It fundamentally reshapes how we understand our own history and the potential future of life, not just on Earth, but within the entire universe.
Absolutely. And hey, we hope you learned a lot from this debate. Who did you agree with? Are you ready to join the search with wide-eyed optimism? Or are you thinking maybe we need to temper our expectations a bit?
Either way, keep looking up, keep asking questions, and remember the universe is almost certainly full of surprises.
Thanks for joining us on The Language Years. Until next time, keep exploring, keep learning, and definitely keep that sense of wonder alive.